Topic 5, the next topic under waves, waves and the particle nature of light. Now here we have waves involving light. So 5.3 optics. So this is the math you will need for this. Let's go through the first subchapter, 5.3.1 refraction. In the O-level class also you would have learned about reflection, refraction, diffraction, interference. Okay, so we will start with refraction here. By the end of this section you should be able to understand what is meant by refraction. What is refraction? Understand how to measure the refractive index of a solid material. So this is something you can have in the unit 3 paper, measuring the refractive index of a solid material. So it's basically like an experiment. Okay, so we will I will show you. Okay, here it is. The next one, use the Snell's law equation relating to refraction. Snell's law equation relating to refraction. When refraction, when waves pass from one medium into another, there is a change in speed. The frequency remains constant. Now keep this in mind. When it goes from one medium to another medium, it can be water waves, it can be light waves, the frequency remains constant. Okay, we have the equation V equals F lambda. So in that equation V equals F lambda, if F is constant, then when the wavelength decreases, the wave speed should decrease. Okay, you can remember the equation V equals F lambda. Now remember here, when it goes from one medium to another medium, the frequency remains constant. So that means when the wavelength or when the wave speed decreases, the wavelength should decrease, or if the wavelength decreases, the wave speed should decrease. When waves pass from one medium into another, there is a change in speed. The frequency remains constant, so the change in speed causes a change in wavelength. Alright, so here I have written it down. If the frequency remains constant, for example, when the wave is going from one medium to another medium, if the frequency is constant, so if it, for example, in the case of light, if it goes from a less dense medium, also called a rarer medium, to a denser medium, then the wave speed decreases. So if the wave speed decreases because the frequency is constant, then that means the wavelength should decrease. This is the wave equation, V equals F lambda. You should know this equation. And you can also see the wavelength decreasing here. These black lines are the wave fronts, are representing the wave fronts. Okay, so from one wave front to the adjacent or the next wave front, that distance is a wavelength. Okay, so you can see the distances here are greater than the distances here between adjacent wave fronts. That means the wavelength here is less than the wavelength here. The wavelength is the distance from one wave front to the next wave front. Okay, so the perpendicular distance between these black lines, that is the wavelength. Okay, so here you can see when the wave is going from air to glass or water, here it's air, here it's glass or water, the wave speed decreases, the wavelength decreases, frequency remains constant. If the waves are approaching the interface is the boundary, okay, between the two materials or two mediums or media. Plural of medium is mediums or media, but actually the correct word is media, but to avoid confusion in the past papers they say mediums. If the waves are approaching the interface or the boundary between the two media or two mediums at an angle, so you can see it's not striking it head on, it's not coming at 90 degrees to this surface, it's coming at an angle, then the change in speed causes a change in direction as well. This is called refraction. Now if this wave or this green line is called the ray, remember ray is perpendicular to the wave front. You have to know this. Okay, the distance between adjacent wave fronts is the wavelength. The wave fronts and the ray are perpendicular to each other. So this is a ray. Why? Because it's perpendicular to the wave fronts. The green line or green arrow is the ray. The black lines are the wave fronts. They are perpendicular to each other. Similarly, over here, this is the ray and these are the wave fronts. So, if the waves are approaching the interface between two media at an angle, then the change in speed causes a change in direction as well. This is called refraction. Okay, one more thing I wanted to mention is, instead of coming at an angle, if it comes along this is called the normal. Okay, the normal is always perpendicular to the boundary, to the interface, to the surface. So interface, surface, boundary all mean the same thing. So we have this normal. Okay, if the ray comes along the normal, so the wave fronts will then be perpendicular to the normal, to the ray. Okay, so imagine this wave is coming like that, this way. Then what happens? Now again there is a change in the medium, so there will be a decrease in the speed, but there won't be a change in direction. The wavelength will decrease when it goes from air to glass or water. The wave speed will decrease, the frequency remains constant, the wavelength decreases, but there won't be a change in the direction if the ray or waves come along this. Okay, the waves are traveling in this direction. The green line, green arrow indicates the direction. This part of the wave slows down first because it strikes here first. Okay, the waves travel more slowly in this medium. The waves end up traveling in this direction, glass or water. When there is a decrease in the speed, when the waves go from one medium to another, it will then bend towards the normal. So this dashed black line is the normal. You can see the ray bends towards the normal. The ray bends towards the normal if the waves go from a rarer medium, also called a less dense medium, to a denser medium, and as a result there is a decrease in the speed. The change in speed is a decrease in the speed, which causes the ray to bend towards the normal. If it goes from a denser medium to a less dense, or in other words rarer medium, then the speed will increase, right? So then it will bend away from the normal. The ray will bend away from the normal. Now here you can see medium 1 is less dense than medium 2, so the ray bends towards the normal. Wave speed depends on the medium, and refraction is caused by a change in medium changing the wave speed. So wave speed depends on the medium, and you have also learned light travels at different speed in different media or mediums. In air it travels faster than in glass. In vacuum it travels even faster than air, and it travels faster in water compared to in glass. Okay, light. But sound is different. Okay, sound in other case, mechanical wave, it will travel faster in solids, slower in liquids, and slowest in gases. So in the case of sound it's the opposite. When the medium is from solid to gas to liquid to solid, the speed increases if it's a sound wave, but in the case of light waves it decreases. Any ray crossing an interface along the normal lines does not change direction at all, as the wave fronts are parallel to the edge, and so their wavelength is equally changed along the length of the wave front. If the wave front is at an angle to the interface, then the part of that hits first, will change speed first, and the wave front becomes bent because different parts of it are traveling at different speeds. So this is what I mentioned earlier. Okay, so any ray crossing an interface along the normal line. Okay, so if that ray comes along the normal line, does not change direction at all, as the wave fronts are parallel to the edge. So if this ray is coming this way, then the wave fronts are, we can imagine like it's vertical, right? So it's parallel to the edge, and so their wavelength is equally changed along the length of the wave fronts. Okay, the changes in direction caused by refraction are the basis for the functioning of lenses and can lead to optical illusions. You can see that over here. See, this part is above water, this part is underwater. So you can see it's as if it's bent or broken. So that's what they mean here. If the wavefront is an angle to the interface, then the part of that hits first will change speed first, and the wavefront becomes bent because different parts of it are traveling at different speeds. The changes in direction caused by refraction are the basis for the functioning of lenses and can lead to optical illusions. A measurement of the amount of refraction caused by different materials is called the refractive index, and its symbol is simple n. The refractive index n is equal to the ratio of the speed of light in a vacuum to the speed of light in the material. Okay, so you should know this. The refractive index n is equal to the ratio of the speed of light in a vacuum, see, to the speed of light in the material. So this is the speed of light in vacuum, this is the speed of light in the medium. So that ratio is the refractive index. Whilst it is difficult to measure the underlying change in the speed, at least for light waves, the effect on direction can be measured easily. I was reading this part. The relationship between the direction and refractive index is given by the Snell's law. So this is the Snell's law. Now you can see this and this diagram to help you understand it better. Okay, so you have refractive index n1 of this material, and the angle here, this is also called angle of incidence. Okay, angle of incidence. This is the angle of refraction. Okay, so medium 2 is here, the light brown color or peach color here. Then refractive index n2. So this is angle 2 n2, this is angle 1 n1. Okay, the values of n1 and n2 are the refractive indices. Again, you can see the plural of index is indices, and the refractive indices in each medium. So n1 and n2 are the refractive indices in each medium. So medium 1, the refractive index is n1, medium 2, the refractive index is n2. The values of theta 1 and theta 2 are the angles that the ray of light makes to the normal, to the interface. So between the this is the interface, by the way, and this is the normal. The black vertical line is the normal, this black horizontal line is the boundary between the two media, which is called the interface. Okay, to the normal, to the interface between the two media at the point the ray meets that interface, as shown in figure C. Okay, so this is the normal that is to the interface. That's why they say to the normal, to the interface between the two media. Okay, learning tip: and in any optical system, light rays will follow exactly the same path if they are transmitted back from the end in the reverse direction. This means the angles involved in refraction are the same whether the light moves from the less dense medium into the more dense one or vice versa. Remember though, apart from rays along the normal line, the angle to the normal will always be larger in the less dense medium. So you see, when it goes from a denser medium to a less dense medium, another word for less dense is rarer, okay, rarer medium, then the ray will bend away from the normal. Okay, worked example: what is the angle of refraction when a light ray passes from water, this is the refractive index of water, into glass, this is the refractive index of glass, hitting the interface between the two at an angle of 48 degrees to the normal. Okay, so hitting the interface between the two at an angle 48 degrees to the normal. Glass hitting. Okay, so this is the equation. Now you saw that Snell's law equation here. You can compare this equation with this diagram. So you know n1 is here, theta 1 is there, medium 1, n2 is here, theta 2 is here, this is in medium 2. We are using that. Then theta sine theta 2 equals n1 sine theta 1 divided by n2. n1, that is 1.33, and sine 48 degrees, and it's mentioned here, into the glass hitting the interface between the two at an angle 48 degrees to the normal. Okay, so we can consider n1 to be this one. Okay, so first medium n1 is here, first medium. Okay, that is water. So imagine this is water, and this n2 is for glass. So imagine this is glass, medium 2 is glass, n2 is 1.50, that is the refractive index of glass. Hitting the interface between the two at an angle. Okay, so it's hitting means it's coming this way. This is the one that is striking the surface or the interface or the boundary between the two surfaces. So this is the angle, that is 48 degrees. Now you have to remember this equation and apply very simple, n1 sine theta 1 equal n2 sine theta 2. Now this is theta 2. We are supposed to find theta 2. What is the angle of refraction when a light ray passes from the water, n1 into glass, n2. Okay, so 1.33 into sine 48 divided by 1.5. So we get this, and we take sine inverse or arc sine of this. That will give us 41.2 degrees. 41.2 degrees is the answer. So this angle here is 41.2 degrees. Okay, so what have you learned so far? You have learned what is refractive index. You have learned the Snell's law. You have learned how to apply the Snell's law into a certain situation. You have learned about wave fronts. You have learned about wavelength being the distance between adjacent wave fronts. You have learned about ray. Ray is always perpendicular to the wave fronts. And then you have learned about refraction. You learned what is refraction. Okay, there is a change in speed due to the waves going from one medium to another medium. And if we scroll down, we can actually see here refraction is a change in wave speed when the waves move from one medium to another. There is a corresponding change in wave direction governed by Snell's law. So these are the definitions, refraction definition. And then we also learned refractive index definition. Remember over here it was there, the refractive index n is equal to the ratio of the speed of light in a vacuum to the speed of light in the material. Now let's see it here. You have the equation in words also that is showing the definition of refractive index. So remember, it's always from vacuum to the medium. Speed of light in vacuum divided by speed of light in the medium. Refractive index n can be defined in several ways, but it is fundamentally a result of the change in wave speed. Fundamentally result of change in wave speed. So refractive index, speed of light in vacuum divided by speed of light in the medium. This is the equation with symbols. N equals C. Remember, we use the letter C for speed of light in vacuum. Then V can be speed of light in that medium. Then this is the Snell's law. Remember, N1 sine theta 1. So 1 here, 1 here. Then again 2 here, 2 here. So N1 sine theta 1, N2 sine theta 2. The values of N1 and N2 are the refractive indices in each medium, and the values theta 1 and theta 2 are the angles that the ray makes to the normal. So remember, it's the angle between the ray and the normal, not the ray and the surface or interface. So see, it's the angle between the ray and the normal. Ray and the normal. This is called the angle of incidence. This is called the angle of refraction. You have learned this in the O-level class. our IGCSE classes. Makes to the normal to the interface between the two media at the point the ray meets that interface. So you have learned all this now: refraction, refractive index, Snell's law, how to apply Snell's law. You have learned about wave fronts, you have learned about ray, you have learned how the speed changes. You remember that you learned the frequency doesn't change when waves go from one medium to another medium. The frequency doesn't change. Okay, here is the experiment. Like I said, you can have this in the Unit 3 paper, investigating refractive index. Using the equation for refractive index with experimental measurements will allow us to measure the refractive index of a material. As long as we know n for the other material, we usually do these experiments with air as the known material, as the speed of light in air is virtually unchanged in comparison to a vacuum. We take the refractive index of air to be n air. This means the refractive index of air equals 1.00. So remember, it's the refractive index in vacuum divided by the refractive index in the certain material. Now in the case of air, refractive index is the speed of light in vacuum divided by speed of light in the medium. Now in this case the medium is air, so it approximately the speed of light in vacuum is the same as speed of light in the medium. That's why you get 1. Now again, if we look at this equation, speed of light in vacuum divided by speed of light in medium, so this will be 3 into 10 to the power of 8. This will also be 3 into 10 to the power of 8 approximately. So that's why when you divide, it will be 1.00. Okay, so I think that is understood. You can read this again if you don't understand it. And this is the diagram picture, measuring angle of incidence and refraction in order to find the refractive index of a material. So this is the angle of incidence. See, it's between the normal and the ray. This angle here is the angle of refraction. Again, you can see it's the angle between the refracted ray and the normal. This is the boundary. You can see here it's one material. Here you can see it's another material. You can see a reflection here. Here you can't see a reflection. So this is air. This is air. And this is some other material. Maybe it's glass. And remember also, we take it from air because the refractive index of air is 1. In this way we can investigate refractive indices. Measuring angles of incidence and refraction in order to find the refractive index of a material. Using a setup like that shown in figure D, we can take several different measurements of the angle of incidence, theta 1, this one. So we can vary this and measure that and get the corresponding values of the angle here, and the corresponding angle of refraction, theta 2. The block used should be an exact semicircle. So you can see here semicircle. Now later we will learn about total internal reflection also, why we are using a semicircle. You will see the block used should be an exact semicircle. Semicircle means half of a circle. See, half of a circle. And we aim the ray to meet the glass at exactly the midpoint. So see, this should hit the midpoint of that glass block. Okay, midpoint of the flat side. This means that the ray passing through the block will be traveling along a radius of the semicircle. See, when it's coming from the center going like this, that will be a radius of the semicircle, and will leave the glass exactly along the normal to the circular edge. See, when it goes like this, you know the radius and the circumference make a 90-degree angle. For O-level IGCSE Mathematics, you would have learned this. The tangent to that point. Tangent is a line just touching the curve or the circle at that point. So the tangent and the radius are perpendicular to each other. Tangent to a circle and the radius to the circle at that point where the tangent touches the circle or the circumference of the circle, then the radius and the tangent make a 90-degree angle at that point. So this means that the ray passes through the block will be traveling along a radius of the semicircle and will leave the glass exactly along the normal to the circular edge. See, along the normal to the circular edge, because this radius is normal or perpendicular to the part of the circumference there. So this will be going along the normal. The ray will be going along the normal as long as you send the ray like this and it strikes the middle, and this is a semicircle. And we leave the glass exactly along the normal to the circular edge. So the only change in direction occurs at the flat side of the block. Comparing the equation we have for refractive index with the equation for a straight line. Okay, then we have this. So equation for refractive index with the equation for a straight line. Now remember the Snell's law. We learned it in the previous page. This is Snell's law. So we write that equation here, and N1 is what? The refractive index of air. Now again, if you don't remember this, you have to refer this diagram. See, N1 theta 1, and then look at this equation, N1 sine theta 1. Okay, medium 1. So for medium 2, this is N2 theta 2. This will be N2 sine theta 2. Okay, let's see. Using a setup like that shown in figure D, we can take several different measurements of the angle of incidence theta 1 and the corresponding angle of refraction theta 2. I already explained this. The block used should be an exact semicircle, and if we aim the ray, okay, so again quickly, ray to meet the glass at exactly the midpoint of the flat side, this means that the ray passing through the block will be traveling along a radius of the semicircle, and we leave the glass exactly along the normal to the circular edge. So the only change in direction occurs at the flat side of the block. Comparing the equation we have for refractive index with the equation for straight line, so I think this is clear now. N1 is 1, so that will be 1 there, so 1 times that will be sine theta 1 equals this. Then sine theta 2 is sine theta 1 divided by N2. Now compare it with this, y equals mx plus c. A plot of sine theta 2 on the y-axis against sine theta 1 on the x-axis should produce a straight best fit line that passes through the origin. The gradient m of this line will be equal to the reciprocal of the refractive index for glass. Okay, so if we draw the graph for this, we plot the graph sine theta 2 on the y-axis, this is your y-axis, then you can think this is y equals mx plus c. M is what? 1 over n2. Then x is sine theta 2. Now remember, theta 1 is the independent variable. Okay, theta 2 is the dependent variable. Theta 2 depends on theta 1. When theta 1 increases, theta 2 increases. So theta 1 is independent, is the independent variable, we can say. Okay, but here we are not using theta 1, we are using sine theta 1 as the x, which is the independent variable. Then sine theta 2 is the dependent variable, because that angle theta 2 depends on theta 1. If we increase theta 1, theta 2 will increase. Okay, so to help understand this better, I have created this note. Actually, these notes are available for the paid students. So this is one of the notes. Anyway, I will show it now. So this summarizes everything we learned in this chapter so far. You can see what is ray, what is wavefront, what is wavelength, with the wavelength between is the distance between adjacent wavefront. All these details are here, and then Snell's law is summarized here. Remember, n1 is the refractive index of the first medium, then this angle is theta 1. Okay, so you can see I've added to the diagram. So this is the angle between the ray and the normal, which we call the angle of incidence. I have labeled the normal, I have labeled the interface. Interface is the boundary, also it's the surface of the medium. The separating between one medium and the other, that is the interface, the separation between the two media, the boundary line. And then all this I have explained. So this is the node, this is the other node that I created. Again, you can see this is investigating refractive index. I have added to the node. So we have the first medium here, which is air. The n1 is the refractive index of air. n2 is the refractive index of the medium here, which is glass. So this is the incident ray up to here. Then from here onwards, when the ray is in the glass, that ray here is the refracted ray. Okay, so we have here the angle of incidence. This is the angle of refraction. You can compare it with this diagram, and we have the Snell's law here. So compare this. This equation is very important. Okay, I have put it in the red box because this is very important, the Snell's law, and that's what we are using here. Now in the case of glass, in the case of air, you can see using this equation, this is the definition of refractive index. Okay, so I have underlined it because it's important. The definition of refractive index is here. That is the ratio of the speed of light in vacuum to speed of light in the medium. So this is the speed of light in vacuum, this is the speed of light in medium, and the speed of light in vacuum is approximately equal to the speed of light in the medium. That's why n, the refractive index, sorry, in this case the medium is air. Okay, so the speed of light in vacuum divided by speed of light in air, it's almost the same. So here and here, therefore it will be equal to or approximately equal to 1. So that's why we get 1.00 here. Now we substitute 1 for n1, then we get this. I explained this also previously, and then we make sine theta 2 the subject of the equation. Now sine theta 1, we take it as x because it's the independent variable. Now theta 1 is the independent variable. Now in this case of the graph, since we take x to be the independent variable, sine theta 1 is the independent variable. Theta 2 is the dependent variable, so we take sine theta 2 to be the dependent variable. Why? Because theta 2 depends on theta 1. So that's why theta 1 is the independent variable and theta 2 is the dependent variable. Okay, so this equation I can write it like this: sine theta 1 over n2. I can also write it as 1 over n2 times sine theta 1. Okay, then plus 0. Because there is nothing here, that means it's a 0. So I will write the 0 here so that you can see how this y equals mx plus c goes into this. Okay, so this is your y, 1 over n2 is your m, sine theta 1 is the x, and plus 0. Okay, now we have the graph. This is our y axis, sine theta 2, 1 over n2, that is the gradient of this graph. Sine theta 1 is what is on the x-axis. So we plot a graph of sine theta 2 divided by sine theta 1. The gradient of that will be 1 over n2. Okay, so the gradient is 1 over n2, and if we rearrange this, n2 equals 1 over the gradient. n2, what is that? The refractive index of glass, because the second medium here, you can compare this with this. Okay, this medium is like the medium here. So n2, that is the refractive index of glass. So n2 is glass. I have written it here also, and then we get this. Now remember, sine theta 2 versus sine theta 1 graph, sine theta 2 versus sine theta 1 graph. Remember, this is the independent variable, this is the dependent variable. This depends on this. Remember, theta 2 depends on theta 1. We vary theta 1. We can move this light source in that direction so that it always strikes the center here. Therefore, this refracted ray is like the radius of this circle. So therefore it makes a 90-degree angle at the circumference. Okay, we learned that previously. Then for different values of theta 2, you can calculate sine theta 2 and get the corresponding values of sine theta 1, plot a graph, and it should be a straight line passing through the origin because it's y equals mx plus c, and the plus c, the y-intercept is 0. So you get a straight line passing through the origin. You can find the gradient of this graph, and that will give you the refractive index of glass. Okay, so that's how you find it. Now let's go back here. So that's the end of that. Then we have the last topic, dispersion. In the O-level class also you would have learned about dispersion. This here, where you get the light splitting into its constituent colors, is called dispersion. So here we have refraction and dispersion. See, when it goes from here to here, by the way, you get the colors of the rainbow here as well. So the dispersion occurs at this point, and from here to here you can see there is a change in direction. Here we have refraction. Now here we have refraction and dispersion over here, but here we have only refraction. Okay, let's see. One of the most well-known phenomena in physics is the splitting of white light into a rainbow of colors by a prism, as shown in figure E over here. Refraction affects different wavelength colors differently. Now you have different wavelengths here. Remember, even in the electromagnetic spectrum you have the different wavelengths. Similarly, in the visible light region you have ROYG, BIV. Red has the longest wavelength, violet has the shortest wavelength here. The wavelength decreases from red to violet. One of the most well-known phenomena in physics. Okay, so we went to rainbow colors. Then we have this. What is this? The Snell's law equation. And we have this, which is the definition of refractive index. If you write it in words, this is the speed of light in vacuum. This is the speed of light in the medium. So the ratio of those two will give you the refractive index. And V equals F lambda. So we can replace V with F lambda. If the ray enters a prism from air, okay, if it's air, the refractive index is 1. Our equations become, so here it will be n1 will be 1, so sine theta 1 equals, and for n2 we can substitute this. So c sine theta 2, and then this is n2, so we substitute this here. So this will go for n2, there will be substituted for n2, so it will be c sine theta 2 divided by f lambda. Then if we make sine theta 2 the subject of the equation, we get f lambda sine theta 1 divided by c here. Okay, so sine theta 2 equals f lambda sine theta 1 divided by c. As the frequency stays constant throughout the refraction and the speed of light in a vacuum must be constant, if we keep the same angle of incidence, then the sine of the angle of refraction will be proportional to the wavelength. So remember, f is constant. When it goes from one medium to another medium, f is constant. And also, you know, c is the speed of light. So let's see, as the frequency stays constant throughout and the speed of light in a vacuum must be constant. Now, by the way, c is the speed of light in the vacuum, that is also constant. So f and c are constant. If we keep the same angle of incidence, so f and c are constant, and remember theta 1 is the angle of incidence, so we keep this also constant, then we can see f sine theta 1, c, they are all constant. So that means sine theta 2 depends on lambda. Then the sine of the angle of refraction will be proportional to the wavelength. Okay, I think that's clear, because f sine theta 1, c, they are all constant. So that means sine theta 2 is proportional to lambda. Proportional means if you plot a graph of sine theta 1 versus lambda, it will be a straight line passing through the origin. Sine theta 2 versus lambda, it will be a straight line passing through the origin if one is proportional to the other. If we keep the same angle of incidence, then the sine of the angle of refraction will be proportional to the wavelength. Smaller wavelengths, violet will be closer to the normal in the glass. Violet will be closer to the normal in the glass. Compare this in figure E. So violet has a shorter wavelength, therefore it will be refracted. Here you can see how it's refracted. Okay, you can compare it with this. So shorter the wavelength, lesser will be the angle. Greater the wavelength, greater will be the angle. Light bends towards the normal as it enters the glass. So here refraction occurs, then also dispersion occurs here as well. Light bends away from the normal as it leaves the glass. So that is here, and here light bends away from the normal. By the way, these dashed lines are the normals. On emergence from the glass prism, take care to continue with theta1 as the angle in air. So sin theta1 equal this. Now this is the same equation that we have here. The sine of the angle of refraction theta1 on emergence. So you can imagine this is this direction. Okay, just imagine if we draw a line going like this, starting here, going like this along these same lines which are pointing in the other direction. So imagine this is going in this direction. Okay, then sine of the angle, so theta1 will be the angle of refraction then. Okay, if you see here, this is the angle of refraction. Will be inversely proportional to the wavelength. Smaller wavelengths, violet will be further from the normal in the air. Okay, so which is refracted more? Here you can see, if you draw the normal again here, this is refracted more. Sorry, okay, so the violet is refracted more than the red. See, we can draw a line here, and also we can draw a line here. These two normals will be parallel to each other, but what is refracted more is violet. Okay, so when the wavelength is shorter, we can say, yeah, the angle is greater, right? When the wavelength decreases, yeah, I think I accidentally said it the other way earlier. So what you have to remember is, when the wavelength is shorter, the sin theta1 will be greater. So the refraction is more. Will now be inversely smaller wavelengths, violet will be further from the normal in the air. Compare this with E. As the angle of incidence on emergence are not all the same due to the dispersion. When they first entered the glass, the color spreading effect is amplified, creating the familiar rainbow or spectrum of colors. So here you can see the sine of the angle of refraction theta1 emergence will now be inversely proportional to the wavelengths. Inversely proportional. Smaller wavelengths will be further from the normal in there. Compare this with figure E. As the angle of incidence on emergence are not all the same due to dispersion, when they first entered the glass, the color spreading effect is amplified, creating the familiar rainbow or spectrum of colors. Okay, and then we have the definitions here, very important. Refraction is a change in wave speed when the wave moves from one medium to the other. There is a corresponding change in wave direction governed by Snell's law. Refractive index n can be defined in several ways, but it is fundamentally a result of the change in wave speed. So we saw this equation, refractive index equals speed of light in vacuum divided by speed of light in the medium, and this is the equation with symbols. So if they ask you the definition, make sure you write it in words. If you write it in symbols, you have to say what n, c and v are. Snell's law, n1 sin theta1 equals n2 sin theta2. The values of n1 and n2 are the refractive indices in each medium, and the values of theta1 and theta2 are the angles that the ray makes to the normal, to the interface between the two media. So the normal, that is to the interface. So the angle is between the normal and the ray. So we have the angle of incidence and the angle of refraction, theta1 and theta2, at the point the ray meets that interface. Okay, so that's the end of that lesson. In the next lesson, we can see total internal reflection. By the way, to help you understand this content better, make sure you answer these questions here and check the answers at the back of the book.